So, good morning everybody. I'm Monojit, one of the presenters of the tutorial that you are here to attend. Let's start. I hope some more people will trickle in, but let's not wait for them. And I also know that there are a lot of choices that you had. There are 10, 11 parallel things that are running. So thanks for coming for this tutorial. Though I'm not sure if you all mean to come to, you are in the tutorial which you want to come to. So for that there is a puzzle, solve it and I will know whether you are you will know whether you are in the right room or not. So I'm showing you 5 tweets here taken from different parts of the world. And can you tell me what's common to them? One good thing of having a very small audience is we can have it in a very interacted fashion. So please speak up and come to the front, especially. Since most people are here, I will mostly point at that screen. But so if you want to move, maybe you can move now. Or otherwise if you can see that screen, that's fine too. Yeah, so what's common to these tweets? Correct, so they are all what linguists would call code mixed or code switched tweets. All of them have more than one languages. So English is common in all of them, or most of them, except for 2 of them, I think. This one is not English. This is also something very interesting. Anybody knows what languages are mixed here? Hint is it's coming from Northern Africa. So one of the language is French, which I think a lot of you would have seen. The other one is Arabic. And in the Northern African countries, French and Arabic is a very commonly mixed pair of languages. So this tutorial is about processing and understanding mixed language data. And what we're going to do is first, in next 10 minutes or so, introduce the expectations, set the expectations from this tutorial. Let me start with who are we. So as I said, I'm Monojit, and this tutorial will be presented with me, along with me, 2 other colleagues of mine. So we come from Microsoft Research India and in general Microsoft India. And we have a project called Project Mélange, mélange meaning mixed in French. And in this project, we have been working on code mixing and code switching for both speech and text for around 8-9 years now. We have worked on various aspects, and also we have looked at the product side of things, like the real need in markets where people mix languages, which come through Microsoft. And we work with our product team partners to work on those problems. So with me, there are 2 more presenters. I will quickly ask them to introduce themselves.
Hi, good morning, everybody. My name is Sandeepan, and I work for the Microsoft Development Center in India. And my area of work is machine translation, offensive search engine protection. So that's primarily, so one of these aspects is also important, like code switching, code mixing, to handle in those kind of products.
Hello everyone, I'm Anirudh. So I also work in Microsoft Research India. So my work is more on, code mixing and language modeling and, seeing how we can make it better.
Yeah, so, one interesting thing about Sandeepan is he shipped the code for, which currently if you type any in Hindi-English mixed sentence in Bing and want to translate it in any other language in the world, the code that will run is Sandeepan's code. So he made that model. So with that, let me get into why this tutorial. So the graph on your right is actually the number of papers in ACL anthology that has the words code mixing or code switching or their morphological variants in the title or the abstract. And the numbers are plotted across the years, and you see what's happening. So this is till 2011. So the first paper in code mixing was in 1998. We will talk about this paper in some detail in the second half of the tutorial. It's by Sankoff, a very well-known mathematician plus linguist, who is pioneered one of the theoretical models of code mixing. But you see, the number of papers till 2012 was fairly low, 2013, I would say. And suddenly from 2014, it's rising. It almost looked like the icon for rise, right? Go up, go down, go up, go down. Anybody knows why it goes up in the even years more? There's a workshop called Computational Approaches to Code Switching, which happens every even year. And therefore, you have 20 odd papers every year for that workshop. This is why it goes up. But even then, you see, the total number is quite high now. So last year, there were 59 papers in ACL Anthology with this title. So this seems to be a very hot field. And this is probably just the right time to work in this area, because there has been a lot of linguistic work for last 30, 40 years in this, very little computational work, and all the computational work have just started over the last 3, 4 years. And this is probably a good time to take stock on what we know, what are the open problems, and what are the interesting research challenges. And that's what this tutorial will be about. The other point is industry is also very interested in code mixing. Ourselves coming from industry, we know this very well. So Microsoft released a chatbot called Roo on Facebook in India, and it could chat only in English. But what people responded to the chatbot in, 50% of those were code mixed between English and Hindi. So naturally, Roo would totally be a disaster. It would fail if it could not understand or reciprocate in code mixing. So that's one example. The other example, this comes from Professor Alan Black told me, from CMU, told me this anecdote. So he was talking to somebody from Amazon, some researcher, I forgot the name, asking, code mixing is an interesting problem, telling him that we should solve it, and I think this is important. And the person responded, it's not a question of whether we should solve it. People are already code mixing to Alexa. What do you mean by we should solve it? It has to be there, otherwise Alexa is a failure. And in speech, people do code mix a lot more, right? And similarly, we'll see a lot of posts on Twitter, Facebook are all code mixed. So I did have personal conversations with Facebook that the translator that they have. So earlier they used to use Bing Translator, and at that time we did a lot of analysis for them, how much of queries in Facebook are code mixed and so on, which comes through Bing. Twitter still uses Bing Translator, so we do see a lot of code mix translation requests from Twitter, through Twitter. Facebook has their own translator now, and at some point of time, Facebook was very eager to know how to solve code mixing. So yes, there is a lot of industry, importance, and we see that rising for this problem. So how we tried to, make this tutorial, what are the objectives we thought? And since it's a very vast area, going in depth in any of the things would be very hard. So what we thought, this is what we will try to, satisfy. So we'll tell you how in multilingual societies, languages interact. Because that's the fundamental thing, understanding, that will give you the background for understanding what is code mixing, why does it happen, and questions like that. Then to make you understand that code mixing is difficult and therefore an interesting problem for NLP. So how is it different from other areas of NLP? Be able to appreciate the challenges and nuances of code mix data set creation. Have some idea about the different NLP tasks and research that has been happening. This is important, that some is what I'm emphasizing. We cannot talk about all, given the time. And be able to better, and in a more informed way, design code mix systems. This is very important, design. Because what we see is, when we talk to our product teams and all, most of the time what we don't know is how to design code mix systems. It's not about how to implement. Implementation is fairly simple. You use PyTorch, throw some models, you have the data, it works. Yes, it works. But what kind of problems you are going to solve is the bigger question, right? What would help users? And this is something where a lot more research is needed. And we have done some research, and we'll talk about that today. So I want to emphasize this again here, that ML approaches and techniques for solving code mixing are identical. There is no rocket science there to those you use for solving monolingual tasks. So no point in going in detail for those. What really differs when you come to code mixing is the priorities of tasks may change. So for instance, one of the fundamental and very important tasks for code mixing is language identification. So at word level, given a tweet, let's say for every word you identify the language of the word. Now this problem was not even relevant when people were looking at monolingual tweets only. So you had to identify the language of a tweet, not necessarily for each word. So there are new tasks that has come up with code mixing. Priorities also kind of change. So speech processing requires code mixing more because code mixing is fundamentally a spoken phenomenon. So priorities would change. Data collection and preparation strategies are different. Optimal use of existing resources. So we already have a lot of monolingual resources and we want to optimally use them. So how to do that? And as I said already, user-centric design of code-mixed NLP system is another thing where we differ a lot from how we actually design and understand monolingual systems. So these are the things we would like to emphasize and highlight through various examples, case studies, and so on. So setting up the expectations, mixed expectations. So we are going to talk only about text. Unfortunately, I'm not a speech person, and my colleague Kalika was going to come and give this tutorial along with me. She unfortunately had to undergo a surgery 2 weeks ago and couldn't come. So thanks to Sandeepan and Anirudh who saved me from talking for 3 continuous hours. So she's a speech person, so we are not going to cover speech. Then we are talking more about design and not much about implementation. There will be a lot of deep, I hope deep, linguistics theory, but not much deep learning. So we will expect you all know deep learning because we will refer to deep learning systems quite a bit, especially in the second half. But we won't get into explaining those systems and how they work. We are trying to map the field but not cover all research. So what do I mean by map the field is what are all the significant areas where people have worked on, where are the gaps and so on. But we won't take each paper and talk about it in detail. Of course, it's not possible, as you can understand. And since we are from industry, we will try to bring in a lot of insights from the industry. If you have questions there, I would encourage you to ask those questions. I mean, maybe not everything we can answer in detail because of privacy concerns or other issues, but whatever we can, we will certainly answer. But we are not going to talk about how to build large-scale systems and things like that. Outline of the talk, of the tutorial would be like this. So prologue is just what I finished. So after that, we'll get into definitions of some of the linguistic definitions and primers of what is code switching, how does it differ from different kinds of linguistic mixing situations, etc. Where does it happen? Then we'll talk about the challenges and solutions. Then we will give a bird's eye overview of state of the art in various NLP tasks for code mixing. After that, we'll have a break for 30 minutes. In the second half, we'll start with data and evaluation techniques. Then we will do language modeling and word embedding in great detail because I believe if you can solve language modeling and word embedding kind of problems very well, you essentially solve code mixing because the way NLP works these days, depending on, based on that, this is my feeling. So we'll do this in quite some detail. Then we'll do pragmatic and social functions of code switching. This is my personal favorite. Why do people code switch? And trying to model that and understand that. There has been very little computational research, but fascinating linguistic research in this. So we'll cover some of them. And we'll wrap up after that with an interesting situation that imagine that chatbots could code switch, what would happen? So we did some research on that, and I will try to end up with this future vision. So before moving to the next, the first content section, what is code mixing? If there's any question, any request that can you do this or do that, I want more detail on this, you can say. And please feel free to ask questions at any time. This is a small audience, so we can be very interactive. Okay, no questions. So let's try to, charge up a bit and add to the energy of the room. So I will. Yep. Yeah. Sorry, I can't hear you.
Are the slides available? available online?
Not right now, but we certainly plan to make them available online. Yes. Anirudh, can you pass a sheet of paper where people can write their name and email addresses so that we can send the materials to everybody who attended the workshop? Okay. So I'm going to play. Okay, so I'm sure all of you would have heard some version of the song or the other, but do you think this is code mixing? How many of you think this is code mixing? Okay, some of you. So suddenly there were two languages, English and Spanish here. I personally, from NLP perspective, I'm not getting into a linguistic debate here, although we will get into that in a moment. But right now, I would say from an NLP perspective, the processing tools you need for processing this kind of data would be what I would call multilingual processing. So you need something which can process both English and Spanish, but not necessarily the two in a mixed way. So English part is totally separate from Spanish part. And the Spanish part in this case was a translation of the English part. So it's almost like your Europal corpus or some of these parallel corpora where you have multiple languages in a document, they are almost translations of each other. Now we are getting into a completely different kind of language and situation now. Look at the subtitles here because you may not know this song. So how many of you have heard this song before? Okay, I see only Indian hands here. So any guess which language it is? One is English, the other language. Did you see any other language though? Anybody saw any other language in this song? Which language was this song in? Do you think it's in English? No, I see some heads nodding saying no. What language? So people from India who raise their hands, do you know which language? Hindi? Telugu? You could say so. It's actually Tamil, but the vestiges of the other language that's present here along with English, both Telugu and Tamil being very similar, so you can't probably distinguish. So I will take Telugu also as a right answer. So Tamil or Telugu, which is a South Indian language. But is it Tamil? I mean, a Tamil speaker won't understand this. An English speaker won't understand this. What is this then? So what is happening here is something very interesting. So you see, all the phonology, the pronunciation is transferred from Tamil. So cow, love, instead of love, cow. So all the phonology is transferred from Tamil. All the morphology is transferred from Tamil. Glass la scotch, in the glass, scotch. Handle a glass, in the hand, glass. So this la is a Tamil morpheme for in. So the morphology is transferred from Tamil. The word order is transferred from Tamil. But all the words are English. All the content words are English. So this is a very complicated situation. I don't know how linguists would characterize this. It's close to something like a Creole language, and often many people have referred to this kind of languages as fused lect. So it's neither Tamil nor English nor code mixed. It's just a mixture of the two language and the language in itself. And this is the last video that I'm going to play. This is again from a Hindi movie, but I think you will be able to follow most of the conversation. See the subtitles, but also otherwise you will understand.
Smile करते extra friendly थी ना?
That was normal.
Huh?
That was normal.
No, खाना पीना normal, हंसना. इतने अच्छे hosts थे आपके ये मीना जी, फिर आप ऐसा क्यों किया? सर पे बोतल पैमाने. मीना जी.
I'm really sorry. इसको इतनी जोर से लगी. I didn't intend to. किसको अच्छा लगता है सर? कोई इस तरीके से छुए जबरदस्ती.
Did I say anything more?
Okay, so in the subtitles, I have marked the Hindi parts, the translation of the Hindi parts within square brackets, so you could have made it out, right? And a lot of the English, I'm sure you would have made it out even without the subtitles. There was very clear English there. So this is what exactly happens in conversational code switching or code mixing. So you see how the two people are going back and forth between English and Hindi. Right? There is no, I mean, as if there is no gap, no pause, very fluently going between the two languages. And even within English or the Hindi, you see English words like hosts, extra friendly, smiling. I had marked those words separately. So they were used. So this kind of flow is what is a more typical example of code mixing that happens. So I think this is something which comes up again and again, and I would clarify it. So you would have heard both the terms code mixing and code switching. And there is a lot of argument whether they are same, different. So according to one definition, code mixing, so there is this notion of matrix language. So any sentence can be assigned to a dominant language. Typically the verb, the main verb defines the dominant language, or the word order defines the dominant language. And then within that, you can have words from other languages put inside it. So this is called the embedded language. So there's a matrix language and an embedded language. So for instance, if you see the right side example, the first sentence, right? Ms. Minal, were you smiling and being extra friendly? So the word smile and extra friendly are in English, but the sentence as such is in Hindi. So Hindi would be the matrix and English would be the embedded language here. Now, code switching is defined as a case where the matrix language changes between clauses or sentences, but there need not be any embedding. Most of the time they assume there is no embedded language, but it's all pure single language, but the matrix keeps changing. So that particular language keeps changing. Whereas code mixing is where there is an embedded language also. So code mixing in some sense is a more general case of code switching, I would say, if you go with this definition. But for most part of this talk, we will not make any distinction between switching and mixing. So we will essentially use both the terms interchangeably. That's what the trend in the computational literature I have seen as well. People don't distinguish. Sometimes people do say intersentential mixing and intrasentential mixing. So language changes across sentences versus language change in the same sentence. So if you try to compare these three examples that I gave, what's happening is something like this. So when two languages interact in a multilingual society, a lot of things happen. So at a very fundamental level, we have what we call transfer. So there can be transfer of syntax, transfer of phonology, transfer of words. Now, in the middle song, the Tamil-English case, you saw a lot of those examples of transfer, right? Now, when the transfer is very high, there is a cognitive integration, as we say, in the mind. So the speaker does not differentiate between the two languages anymore in the mind. So that is what I call by cognitive integration. Whereas when the cognitive integration is low, the speaker is very aware that now I'm speaking in English and now I'm speaking in Tamil. So as the speaker goes on, now I'm speaking in Chinese, now I'm speaking in English, so on and so forth, right? So that's what I mean by cognitive integration, which is your x-axis in this diagram. And The y-axis is the performance integration. On the surface, the language that you see, how much interleaving between, how much mixing is happening. So if the interleaving is very frequent, I would say high performance integration. If the interleaving is very low, then I would say low performance integration. Now let's take the first case, the first song, Despacito. What was happening? It was very clear that these are two distinct languages. In fact, these are sung by different people and all, right? And there is no interleaving at all. You just have one switch point, the whole English and then the whole Spanish. So these are the situations which I call a multilingual discourse. So I would not call it a code switching or code mixing per se. Let's see the other extreme. So very high integration at cognitive level. You don't even know that this is another language. But you don't mix very frequently. When does it happen? So in borrowed words. So, I mean, if you take English as an example, now when I'm speaking English and using the word chandler or chauffeur in it, I never think I'm speaking French. I don't even know that these words came from, most English speakers may not even know that these are coming French words, right? But actually they are French words. So this is borrowing or loan words, which is the other end of the spectrum. In between, there are a variety of things, and I would say code switching is somewhere here, where and code mixing, where you are pretty clear that you are talking two languages. And your mixing also shows that you are mixing two languages, your pattern. So there is a medium level of integration, both at the cognitive and performance level, between the two languages. And then when the integration becomes very high, in your mind, as well as the frequency of interleaving and all, this becomes an altogether new language, which was kind of the Tamil song, right? Every alternate, so English word, Tamil morpheme, English word, Tamil morpheme, English word, Tamil morpheme, like that. Even cognitively, you can't differentiate that, you can't identify that language either with Tamil or English. So this is what I would call a fused lect. And there is a lot of interesting studies about fused lects, and there was a very interesting paper which said, they tried to prove that Hindi-English mixing in India is not code mixing, it's a fused lect. It's a new emergent language. Okay, but not getting into there. So we will come back to this diagram again and again, because it's very important to keep these things in mind when you are designing technology solutions. So you have to identify where your case lies in this continuum. But as I should also emphasize, this is a continuum. So the words like, where code switching ends and where code mixing begins, or where multilingual discourse ends and code switching begins, are not clear at all. I mean, there are no sharp boundaries. In fact, we had done a work to show that there is no clear boundary between mixing and borrowing. It's very hard for a lot of words to say whether it's a borrowed word in a language or not, because borrowing is a long-term diachronic process. And the other thing I want to emphasize here is code mixing or code switching is a phenomenon of multilingual societies. And how does it differ from multilingualism? You would say somebody is multilingual if that person knew more than one language. And let's say if you look at a country like, say a city like New York, it's highly multilingual. There are a lot of people speaking a lot of different languages. But is it a multilingual society? Probably not, because it's not the same set of languages which all the New Yorkers speak, right? Contrast it to the example of Hong Kong. So if you see that, these are from Wikipedia, and if you see number of speakers, native speakers of different languages in Hong Kong, Cantonese is the highest, followed by English, and then there are other languages. But this curve is interesting. So in 2016, 94% of the population could speak Cantonese very fluently in Hong Kong. 53% could speak English fluently. So this easily shows that at least 50% of the Hong Kong population right now speaks both English and Cantonese. That is a multilingual society. They know both the languages and they can mix it. In fact, they can also speak Mandarin. Another 50% speaks Mandarin. So Hong Kong is, a lot of linguistic studies have been done on Hong Kong, both sociolinguistics and theoretical linguistic studies, where they wanted to see the language mixing patterns between Mandarin and English, Cantonese and English, and Mandarin and Cantonese, as well as three-way mixing. And if you are interested, I would recommend you go and look at the Wikipedia article. It itself has code switching in Hong Kong. It itself has references to situations where, why Hong Kong people are so keen about using English. That's because they want to establish an independent identity from the mainland China, where Mandarin is the main language. So here, that's why you see over the years, the English speakers in Hong Kong has been going up. So there are interesting sociolinguistic studies on that. And before we move to the next part of the talk, or wrap up with the linguistic primer, these are some of the things we want to remember throughout the talk. So one is code mixing mainly happens in multilingual societies, and actually it may not be wrong to say it happens in all multilingual societies. Multilingual being defined as, society being defined as every member of the society speak the same set of multiple languages, or a large number, not necessarily every member. It is predominantly a spoken language phenomenon and usually associated with informal conversations. There will be rarely a case where in a formal conversation people use code mixing. When people start doing that, it almost becomes a fused leg. A very beautiful example of this is when Indian Prime Minister Narendra Modi gave a talk in the United Nations, he was code mixing all the time. So it's another evidence that probably Hindi-English mixing is no longer a mixing but a fused leg. But that aside, the last point is code mixing has very well-defined socio-pragmatic functions as well. That might vary, these functions might vary from geography to geography, situation to situation, but it does have. So it's not a random phenomenon. So we'll move to the next part. Why do we care? What are the challenges and solutions? But any questions till this? Okay. So why do we care about code mixing? The simple answer is, all the technologies, language technologies that we have built for a single language fails for code mixing. So if you have a digital assistant like Cortana or Alexa, it's very likely that somebody will ask in Hong Kong in English Cantonese mixed, phrasing when they are putting a query to the digital assistant. So unless you tackle code switching or code mixing explicitly, it will fail. Translators, we have seen a lot of queries to Bing coming which are code mixed, mostly from social media. If you want to do any kind of social media analytics, you have to tackle code mixing. We'll see in a moment how much of social media data is code mixed in various geographies. So obviously we want to do something about it. There is a need for it. In fact, I can tell you a small anecdote here. So when we started working on code mixing around 8-9 years ago, people appreciated it as a very interesting problem, but both internal and external reviewers, internal to Microsoft and external reviewers told us, oh, this is interesting, but this is a edge or peripheral phenomenon. This happens only in India. Those kind of comments we heard. And of course, we tried to argue with a lot of evidence from linguistics and other studies I will show in a moment that no, it doesn't happen only in India. It happens all over the world and things like that. And the situation remained like this till, I think in 2016, Microsoft released Skype speech-to-speech translator. The first one was between English-Spanish, and it worked wonderfully in the lab setting, and in the wild, it failed pretty miserably. And they were thinking, what happened? Why did it fail? And when they analyzed the log, they saw that nobody was speaking Spanish or English. Everybody was speaking Spanglish. And you can relate to it, right? So when you go to Spain, when I go to Spain and I don't know Spanish, but I would try to connect to them by saying the few Spanish words I know, hola, si, kind of things, right? So that was what people were doing all the time when they were chatting to the other person. Just to connect, they were using Spanish person was using English, the English person was using Spanish. So it failed. So that's when they said, oh, this is super important. You should work more on it. So just an anecdote. So when we tried to justify that code mixing is important, we thought, okay, let's see how much code mixing is there. And at that time, this is back in 2014, there was no large-scale studies, so we didn't have data on how much posts on Facebook, for instance, are code mixed. So this study that we had done, mostly for pages related to India, we saw that all sufficiently long threads were multilingual. I'm very precise here, multilingual, not code mixed. So meaning they were in more than one languages in the thread. But 17% of the posts were code mixed. In the single post, there were multiple languages in 17% of the cases. 17% is a huge number, right? If you are thinking of a big social media platform like Facebook. In 2017, we extended this to actually 7 European languages. So the previous one was mostly Indian language study and also mostly Hindi and English. So we went to 7 European languages, I think English, Spanish, Portuguese, French, Dutch, German, and Turkish, and tried to see how much of mixing is there on Twitter in between these languages. So we had to build word-level language labeler for that. And what we found is overall, 3.5% of the tweets were approximately code switched. And then we did an analysis city-wise, in which geographies code switching happens more. So the way to read this graph is each pie has different colors for different languages. There's a white portion, missing portion of the pie, which is the code mixed part. So bigger the missing portion, the wedge, the white wedge, the more the code switching. And you can see places like Istanbul and all has lot of code switching. It's like, if I remember the number correctly, it is 13% or something. Quebec City has lot, Mexico City has lot, Madrid, Paris. But on the other hand, some of the other places like London, Houston, New York has not that much code switching. I think Houston had the list with 1.2% or something. We'll come back to this. But essentially what it shows is, at least 1% code switching there is in most places of the world, and some places as high as 13-14% on Twitter. Anybody can answer this question, why on Facebook we see more code switching than on Twitter? Facebook numbers were significantly higher than this, right? So the reason, I think, is Twitter is a broadcast medium. So conversations happen, but only in small pockets in Twitter. But most of the time, you're broadcasting to the world. And then it becomes a more formal communication, closer to formal communication. And Facebook is more closer to informal communication. And as we saw, code mixing is more informal communication. So yes, code mixing happens a lot. But is that an enough reason? Are there something more interesting that we can say about code mixing? So we did this study, actually, where we tried to see why people code mix in English in the bilinguals, why do they, and when do they code mix on Twitter? So we collected tweets and tried various hypotheses, and the hypothesis that emerged as the strongest indicator of code switching or language preference is negative sentiment. A tweet with negative sentiment, or a portion of the tweet which had the negative sentiment, had a very high, almost 10 times more chance of being in Hindi than that in that for English. On the other hand, positive sentiment was extremely strongly correlated to English. So you may not understand the title, so I will translate it for you. We might praise you in English, but swearing, we will swear you always in Hindi. So the left side chart shows prevalence of swear words in various languages, English and Hindi. The English part you see is minuscule compared to the Hindi part. So swearing mostly happens in Hindi. So we will get into some more analysis of this kind of things at the end of the tutorial when we do the socio-pragmatics. But this is what it says. This is a very important thing it says. If you are looking at multilingual societies and trying to study trends or things like that, and looking at only one language. By the way, English is the majority language on Twitter for Indian users. 70% of the tweets are in English. So you might think, I will look at 70% and estimate the trends. But you might be totally wrong, because all the negativity that you didn't see in English were actually in Hindi. So that is the driving message here. So it's very important. If we all agree, then why is it challenging? I personally think there are 3 fundamental challenges when it comes to processing code mix data. So the first is the problem of data. As I said, mixing is predominantly a spoken language phenomenon. So you won't have a Wikipedia which is code mixed. So if you think of how we train our big models like, word embedding models today, we mostly use these annotated large amount of text data that we find in web and all. But a lot of them, most of the written text that are found, especially if you are trying to build a parallel corpus, right? Most of the data that you can scrape from the web will be typically non-code mixed. So that's first problem, where do you get your data from? The second problem is that of model explosion. So if you have n languages, you want to build n models for them. Now, if you are talking of code mixing and want to build model for every pair of languages that are code mixed, then you have order n square pairs, right? But code mixing can be three-way also, four-way also. In fact, three-way code mixing on Twitter is not that uncommon. We found around 0.1% of the tweets have more than 2 languages. So if that is the case, then you have order n cube languages. Of course, you can argue, no, all pairs are not mixed, only in multilingual society, so we can see where to, which geographies we are targeting and accordingly build. But still, there is a modal explosion, as you can understand. The third problem is we have already built a tremendous amount of data and models in monolingual, NLP. Don't we want to use them? And the motivation for this is the following. Imagine you know 2 languages, let's say Latin and English, very well. You have never heard anybody mixing Latin with English. But if somebody mixes, would you not be able to understand? Or if I force you to generate Latin and English mixed, would you not be able to generate? Most people do it without any effort. So there must be a way to learn the rules of code mixing independent of the languages being mixed. And this is a question that linguists have been working for several decades, and in the language modeling part, we'll go much deeper into it. But how can we reuse language, resources is the other thing. So here the challenge is more like there's a lost opportunity if we don't reuse the resources. So with that philosophy, right, of reusing resources, let's see what all at a very high level we can do. So of course, you can collect data in a code mixed language and then train a code mixed model from scratch. This will be the most obvious thing to do. And as discussed in the previous slide, right, the 3 reasons I said for which this is not a great way of looking at the problem. What can we do? Can we do better? So one way to solve this problem is what I would call this divide and conquer rule. So what happens is, let's say you get a code mixed text to speech, you build language identifier at word level, and you divide it into fragments of, let's say, L1 and L2, and then separately apply the L1 model on L1 part and L2 model on L2 part, and you get a system. Now, is it a good idea? So first of all, apart from the language identifier, you don't need any code mixed resources here. So that's great. We are only using monolingual resources. But are we losing something here? So by the way, there are work along this line. So in 2014, there was a post-tagger work from our lab where we tried doing this and showed much improvement over some certain baselines. But this is not a very good model, The reason it's not a very good model is the context is lost. So the L2 fragment, which was embedded in L1 context, you won't have that context. And therefore, when you independently try to process L2, let's say for post-tagging, you see the word bank in a Hindi sentence, English word bank in a Hindi sentence or a Chinese sentence. Now, bank could be verb or noun, and you don't know because you now have no context from the other language. So this is not an ideal situation, but in some cases it does help. A slightly better approach is this one. What you do is, instead of running the L1 model and L2 model on the fragments, you run the L1 model on the entire text and L2 model on the entire text first, and take the output of the 2 models. So if you're post-tagging, let's say, you take a code mix sentence and run it through the English post-tagger, run it through the, let's say, Mandarin post-tagger. You get the post-tag output from both the taggers. You also run an LID, so the language identifier will tell you that these words are Mandarin and these words are English, let's say. Now, you take all these 3 and try to combine it in an intelligent way. The simple way to combine it would be, if the LID language identifier says it is English, then use the output of the English tagger. If it says Mandarin, use the output of the Mandarin tagger. So that's a very simple way of combining, and some of the speech processing work use this. So if you are to build a multilingual, automatic speech recognition system, ASR, what you would do, this is one of the 2014 or 15 paper from Google where they ran a speech recognizer for English and, let's say, Mandarin on the entire data, and also ran a language identifier for speech, and then accordingly took the output. Whichever LID system was more confident on whichever fragment, they took output of that one. A much more interesting example, and closer to what we are going to talk today more, is from Solorio and Liu. So Tamar Solorio, she is in University of Houston, and she is one of the pioneer of research in code switching in the ACL community. So this 2008, like 10 years, almost 10 years ago in EMNLP, she had one of the first computational papers on code switching. So this was on pause tagging. What she did is after she got the outputs, these three L1, L2, and LID outputs, there was a little bit of code mixed data that she collected and used that as reference to train a model, a machine learning model, which learned a combination logic. So it learned essentially when to use L1's output, when to use L2's output, given the LID and the word and the sequence. And that actually improved the performance a lot. Actually, in this paper, I think the pause tag accuracy goes to something like 95% for English-Spanish code switching on Bangor corpus, which is actually pretty remarkable. So it was one of the very good and early work on code mixing. But what's the problem here? The problem here is this works fantastically if, the stretches or fragments which are code mixed are long. As soon as the interleaving becomes too short, morpheme level and all those kind of phenomenon comes in, this doesn't work very well. So, and it's not hard to imagine why it would be so. So it's kind of similar to the problems here, but here I would say in this case, divide and conquer, this is a more severe problem than the problem here. Okay. And then the last one is what I would call zero-shot learning. So this is what is more popular these days. So what happens here is you take L1 data, you take L2 data, and you train a common model for L1 and L2 in some, interesting ways. We'll come to what those interesting ways are again in the second half of the talk. But effectively, you get a code switch model without any code switch data. Now, this is with the assumption that, this model that's sitting in between, typically it's a neural net, and it's an embedding system, which is, it's a word embedding or a sentence embedding, which has taken data, seen data from both L1 and L2, and has been able to embed the two in the same space, two languages. So now, you have the same semantic space, let's say, for both languages, and it's very easy to process a code mix data because essentially you are talking of the same space. It's no longer any different spaces. So first work along this line was this zero-shot translation with Google's multilingual neural machine translation system paper, which tried it with 3 languages, English, Korean, and Chinese, or English, Korean, and Japanese, I forgot which 3. And a much recent version of this came in, was it in ACL? NeurIPS. Oh, this EMNLP. This EMNLP. Oh, okay. So it's going to be presented. So watch out for this. So this is like massively multilingual sentence embedding. So where they are doing for 93 languages. And in the first paper, they do mention code mixing, although they don't show any results on code mixing. In the new one, they don't talk anything about code mixing, but I think it has a lot of promise for code mixing. This is an interesting direction. With that, let me wrap up the initial part of linguistic, primer and the fundamental challenges and all. We will go to state of the art in various aspects of code mixing before the break, which I will ask Sandeepan to cover. But you have any question till the part covered till now? No? Okay.
Thanks, Monica. So in this part, we will look some of the state-of-the-art speech and NLP tasks where people are using code mixing and to solve some of the real-world problem as well. So what we are doing is like, there is a taxonomy we have created. So any task, monolingual task that takes input beyond word level or lexical level, that can have a code mixed counterpart of it. So, and it can be subsentential level, it can be in sentence level, it can be in conversational level. So subsententials like query. So there you have either a ill-formed subsentential level or a phrase, and then you have like sentence level task like POS tagging, named entity recognizer, sentiment, all of them. And you have conversational level like chatbots, even like sometimes if you consider like multiple sentences, then machine translation is also in that, like more than one sentence involved, and text entailment. So these are kind of tasks where people are working. But there are, by definition, what I said is like beyond lexical level, but there are work which focus on intra-word level, like morphology and those kind of things. So which is like there are few works done in that. So in the taxonomy, what we can see, like code mix tasks are primarily divided into two applications, like text-based and like speech-based. So speech is like ASR and TTS, where people have worked in code mixing. And in text, like word level task, like one of them is language identification, which is very important, as we have seen already, and part of speech tagging, named entity recognitions. So this kind of tasks, which are like primarily sequence labeling tasks. And then like sentence level task, like where it takes only one sentence and like tries to predict the sentiment, and also like language modeling as well as parsing of the sentence. But there is also the challenging thing, which often take more than one sentence, which I'm like categorizing as application level, because it has like many industrial application as well. Question answering, the question you ask any search engine like Bing or Google, instead of giving a monolingual sentence or monolingual query, you just give a code mixed query. And in machine translation, it's like you are giving a text which is like Twitter or any kind of feed which is multilingual, like code mixed. And also in the information retrieval, like same as like question answering. Here, instead of question, the query is multilingual. So how do you answer this? So these are the primary tasks. So we are not going to cover all of them. Like we'll cover one or two of them, and we'll see like how we solve them. So before that, like here is the research what has happened in these different tasks. So language identification. So these numbers are the number of papers that is cited, that has been published in SCL anthology. But for speech, we are not considering only SCL anthology. We are also considering interspeech and ICASP, because SCL doesn't have like significant representation of speech. So in that sense, like you can see language identification, there is like a lot of footprint in code mixing. Like there are 39 papers in SCL anthology. And whereas like the areas like application areas, Q&A, question answering, translation, they're really low. Like the numbers are really, really tiny. Like almost no work has been done in this area. Now, the areas where we have like large number of paper, like there are a couple of shared tasks, like computational approach to linguistic code switching. That has given a lot of contribution to language identification because of the shared tasks. Similarly, there are shared tasks in ICON on POS tagging and language identification, and sentiment analysis on SAMeval and track as well. So this is what is the current scenario of the NLP task. Now, we'll go into the detail of the ones or two such tasks. Like first and the very important one is like language identification. If we are given a code mixed sentence, we need to identify which language the each and every word is. So so given the sentence like Microsoft ने एक worldwide hackathon organize किया. So this is a code mixed sentence for English and Hindi. And here the task is to label each and every word in the text with a language or from a set of languages, or whether it's a named entity. So the very first word, Microsoft, is a named entity, and then these are Hindi words, and the remaining words are accordingly we need to label. So that's the formal definition of the task. So altogether, this is a sequence labeling problem, like any other sequence labeling problem. So you can also have a baseline, like, okay, I know the dictionary, and I will just search for which word it is like from which dictionary, but that's not going to give you a very good solution. So, and it is very important, as Monojit pointed out in one of the slides, that for any downstream natural language processing task, this is probably the first thing we need to do, unless we are doing zero-shot learning. So here the challenges are, like if we take the examples like Dilwale and Bajirao Mastani, even super films get the Monday Blues. And in the first one, you can see like there are two words which are in green. They are like named entities. They are not really like code mixing. You are using two names which are from a different language, but the entire sentence, like the matrix of this language is English, but there are named entities which are you are borrowing from some other language, which ideally named entities, but they are also like contained word in that language. And in the second example, what an awesome movie was, it was Sabko Dekhna Chahiye. So this is, there like you are borrowing, like there is code mixing, but there are a lot of challenges like spelling variations. So this can happen. Also, there are words which are common across language. So we will see them. So now we'll again referring to this slide, like if you can solve this problem, then ideally what you are trying to do, like you are solving this to circle LID. So if you can solve this, then the remaining thing, like you build a model L1 and L2 for the respective languages, and then you combine in an intelligent way, whatever you want. So typical thing is like you use your favorite sequence labeling task like HMM, conditional random field, or recurrent neural network. And to do that, you have like some data already available. Something like say EMNLP 2014 has like a lot of code switching data set for many languages. FIRE is forum for information retrieval. That also have like a lot of language LID data. Now, once you have this data and you know that I'm going to apply a sequence labeling task, how you are going to do that? So the one way is like, if you do it like a very supervised way, the fast approach which Monojit showed, like then you really need a lot of code mix data. Probably the requirement is even more than when you are trying to solve a monolingual problem. So the question is like, can we use like semi-supervised kind of learning where we have like language data for monolingual NLP tasks, and that can help us really. So one approach we tried is like, we have monolingual label tweets. Monolingual tweets are easy to get. Like that means the tweets are in one language. Though you need to make sure that the tweets you are collecting, they are monolingual. So that you can use many heuristic to get like monolingual tweets. And once you get monolingual tweets, you can build your initial model for the monolingual thing. And then you have like unlabeled tweets. Unlabeled means you are not sure whether there is a code mixing or not. So there is a possibility that these unlabeled tweets are code mixed, but if you do not know which languages the code mixing are, so they're not labeled. And then you build a finer model. So how it happens? Now, so this is a diagram, like a finite state machine you can think as of now. So in this machine, like, so one segment, like I have taken 3 languages, German, French, and English. So German, I have written GE, but if you are, like there is a controversy, people write DE. Like for some reason, I have kept it GE. For the time being, I assume with pinch of salt, it's German GE. Now, so the first one, like if we see, like say, consider the English one. So in a monolingual tweet, there is the possibility that an English word can follow an English word, so which is the self loop, and then XEN stands for like extra linguistic information, like punctuation and other tags like hashtags, and so those kind of things are in the second state. Now, from English you can move to an extra linguistic tag and come back, and within English you can also like go as a, with self loop. Now, I think I should use this one. Now, so now there is a possibility, of course, there may be like multiple extra linguistic information in sequence, but we are combining them all together into one part. So that's why there is no loop here. So this is basically trying to capture the part from the monolingual tweets, like which is monolingual, and then there are these are for multiple languages in parallel, like so either A or B or C. So from this HMM, initially you estimate the probability of this path, and then when you like tune it, you can tune it with these additional edges. That means it's saying, well, after English, a German word can appear, and vice versa. Even the same similar transition can happen here as well. So if that is the case, then you need to re-estimate all these edges. So that means from the monolingual one, you estimate the yellow edges, and from the like unlabeled tweets, you re-estimate the green edges. For example, like say suppose if you just, your initial model, what it will do, it will try to estimate something this kind of for one single state. Like you have English with 0.8 probability goes to English state and goes to the end of the sentence with 0.05, and this one with 0.15. So this is something like your basic transition probability estimation. Of course, it has also like the other emission probabilities, which we are not showing here, which is, but once you have that added, the green line, actually this probability mass, which was 1 here, is now you are re-estimating to the very well-known Baum-Welch estimation algorithm, and you get like, well, some of the probabilities are coming here, like 0.015 to German, 0.015 to French as well. So this re-estimation actually will help you to get like the code-switched model. Now, so this is like a glimpse of the model, how you can build a language identifier using only semi-supervised learning, like you do not have any labeled monolingual data, but still you can work with it. Now, with this, like if you build a system with this kind of system, then you find like, well, there is some like examples where you are doing the right thing and where you are making the mistake. So this is like English and, I don't know, Spanish, yeah. So, and here you see that this green part is the English, which is correctly identified this model. And and here also, like it is between English and Italian, I think, German. So here you can see like this is perfectly identified. Though this was is a token which is common between these two languages. Word is also an English word, but in this context, like they are like what was it's in German. So that's what it is doing correctly. But when you see like here, there. Remember when then the remaining part of it's Portuguese, I guess. So this part it's not doing correctly. So it's a mistake of the system. It's because maybe a very short presence and the initial state of the model is expecting something, but here this kind of mistake happens in the language identification with this HMM-based model. And overall, this work has, like, if we look into the accuracy, like you can, we tried with like 2 to 25, like different possible ways of code mixing. Like if there are only 2 languages, you can see the accuracy is like 96%. If you have 7 languages, that means in your HMM, the transition I had only for like 3 different languages instead of like your HMM grows up to like 7 such parallel transition, and then it goes little down like 94.5, but if you increase like it to 25 languages, but it's 90. So that means it is not dropping significantly, but it's saying like if you have like N-way multilingual or N-way code mix, then there is a possibility that your system requires its system accuracy will drop a little, but at the end, like it's good to use something which is like kind of unsupervised, so that you can extend the language coverage a lot. So that's how like code switching is like the techniques applied for language identification. And now we'll go to like another task, like application, where is the machine translation, where we will see like what is happening with code mixing. Now, so in code mixing, we have seen like Microsoft used to translate tweets from Twitter, and with the analysis of 16 million such tweets, we found 4 to 6% tweets are code mixed. So this is the statistics from Bing Translation. And like the application of machine translation is like when you like say want to do something in speech-to-speech translation using Skype speech-to-speech translator, you will often find that there are people which are speaking like in code mixed languages. So these are not like cherry-picked example or something. These are like real example when we deploy and test like translation system for speech-to-speech Skype translation. So this is the conversational testing, and somebody is saying, हाँ मैं higher education किया हूँ. So here the mixing is this word education, which is this one. So, and if you translate it, you will get something like this. So, but if you try right away in Bing, you won't get this one, because this is something which I'm showing you when we didn't deploy the code mix model. So now the code mix model is deployed. So what I'm trying to say, like, well, industry also have a scope. Industry is deploying code mixed model. But this is what it is doing if you do not develop a code mix model. So this is trying to transliterate it. And transliteration making mistake, probably because it's a foreign word, it has multiple like ways of writing in this script, so it's not doing really great there. And the second sentence, like, मैं अभी तक शादी नहीं किया हूँ, मतलब unmarried हूँ. This is again like not cherry pick. This is a real dialogue. And again, this word unmarried is badly transliterated or translated using the non-code mixed translation system. Similarly here, actually cricket में मुझे अच्छा लगता है. So actually cricket, this is something really bad. Now if you try this sentence again, like in Bing, you can see the current output, how it is currently doing the translation. And overall, so that means like if we just do this like system, which is like this system is fairly complicated transfer-based machine translation system. So that also doesn't do very well for code mixed languages. Now, but here, what is happening? We are giving all the input in one language, like which is like in Devanagari script. But the problem is more intense if the input is given in Romanized, because you have many other variations. So in Twitter, say probably somebody is writing something all in Roman script, and then if you try to translate and build a model, especially from Roman, Hindi to English, then it's even more difficult. But if it is less intense if it mixed script is used. Like say this word, like which are in code mix, you write them in English, which are in English, and the one which is in Devanagari, then you write them in Hindi script, Devanagari script, then it's easy. Because every machine translation model has a copy system. Like it will then only, instead of doing this mistranslation, it will try to copy them. And if it copies them, probably you will get something better blue score. Now, how do you do that? How do you develop this kind of machine translation system? So the easiest way, like the baseline is like, well, you have this is French and Italian, I guess, and you just take one language and tries to translate it into the target language. And what you get, this kind of things is happening. So it doesn't do anything for this word. Now you can really, what you can do is you can segment it in two ways. So you have like French part and you have the Italian part, and you use like corresponding translation system like French to English and Italian to English, and then you do a combination of them, recombination. But if you do that, like here it is not actually code mixing, it's like kind of code switching. If it is code switching, you have enough context to do a good job for individual sentence kind of thing, then that will be possible. But if it is code mixed, then the problem is even higher, I guess, like you cannot. So there what we do is like, so I'm hiding something because of we haven't published this work yet, and we haven't, we are not like good to expose everything. So what we do actually, so if you have like something code mixed, instead of code switching, like French and Italian, they're mixed inside utterance, then you translate this one to the matrix language. Like French and Italian is mixed, so you translate the Italian into French. So French-Italian code mix to French. So that means it is translated into your matrix language. Then you apply this French to English. So that instead of like doing this like in sequence and recombining them. And we are like in the process of integrating for 7 languages, but some of them has already been done. But whatever you do, like here is a quote from Google paper, like you can read it. We can handle input with code switching. This is the zero-shot paper, and in Packtrit it is not too hard to find examples where code switching in the input does not result in good output. In some cases, the model will simply copy parts of the source sentence instead of translating it. So which is happening, like you can see here this is happening, it's copying. So copy model is like really powerful. Like it's, again, here also it's actually copying and transliterating it. So that's what is happening. But finally, I'll show you some results like what we are getting. And this system I'm not going to discuss at all, like how we did it. So this is my Hindi-English means this is basically Hindi code mixed, English to English system. Now, we have like if you run it like the older, like non-code mixed machine translation system from Bing, you get like different accuracy, which is the blue score, separate blue score depending on your like input type, like if it is a Devanagari, like in a particular Hindi script, if it is Romanized Hindi, or if it is a like mixed script. Now, this overall gives you like some decent blue score, and the question may come like why the blue score is so high. The generally blue score you will not find in that range, because these are all the results I'm reporting on synthetic data. So it has like a lot of like the training and test data is like quite homogeneous in nature. So that's why it's like very high blue score here. But also this is also another argument of the high blue score. Like it is your input blue is also very high. So input blue means if you do not do any translation, just say what is my input, that is my output, because it has a lot of code mixed things. So you already have some amount of translation you can see in the source language itself. So that overall like is saying, well, 13 and 12 is my input blue. That means I know already 12 or 13% if you consider is a percent, like a very significant high number of words in the target language. But with our technique, what we are getting, like when the situation is like Romanized, which was like really bad here, you still can get a very reasonable blue score, like 44. And if it is like 44, like which is like Devanagari, which was actually the problem which we showed in the like the example from our data, like in the Skype to Skype translation, we can get like 60 blue score. And here we have like minimal gain. And the reason is here the copy model actually works really better, which being used to do. Like, well, you have mixed script, so you just translate the language Hindi to English, and the English you just do copy. So that basically doesn't create any kind of problem. So this is but how we have done this in one line, like no detail, like we have created a lot of synthetic data, and that synthetic data creation probably will touch something in the second half. That synthetic data will is giving us a lot of code mixed to English parallel data, and that code mix to English parallel data we cannot just really pump into the system easily, because if you just pump into the system, what will happen, it will damage the monolingual accuracy. Or else you have to create two different systems. One will take care of the monolingual input, and the other one will take care of the code mixed output, which is like, whereas like a lot of problem in deployment, like actually you are creating another deployment thread, so you have to spend all the resources. But instead, like our requirement was different. Our requirement was within the single system, it will be able to handle the monolingual inputs without damaging the accuracy, as well as it will do some good on this thing. So that's what we did. So I will leave it here for the next session, and meanwhile, like if you have any question, any comment.
From whatever
Yeah.
Did you compare with zero-shot learning, the code switching? Just asking, did you compare with zero-shot learning?
Yes, we have compared this, but like our accuracies are with this one is like slightly better. The reason is like we have used a lot of synthetic data, like synthetic code mix data, but which was not available, means which we didn't use in the zero-shot learning yet.
Okay. Another question is that if you use the real language instead of using synthetic.
Yeah, so that anyway, like before deployment, like we have the accuracy on the real code mix data. This is something like I just presented from the portion of the synthetic data that we have used, the blue score. But the one like in the slide, like the cherry picked example from the conversation, and there also we have like significant gain. So the one which I reported in the last table, there we have like this accuracies around synthetic data, that's why it's very high. And with this system, like typically it was, when it was so high, that means we have pumped a lot of synthetic data into the system, and that actually damaged our monolingual accuracy. Like if I would have present the corresponding monolingual accuracy drop, there is a drop which is not acceptable to our system. Like we cannot accept any drop, like even a delta drop. But the one which we have deployed, we had to first fix that, well, there is no change in the monolingual accuracy, which is more important. And then we have like this thing, and there also we get like 5-6 blue point improvement on the real test data for like real code mix test data.
Since there are no other questions, I will, think of other questions. Meanwhile, I will add to what Sandeepan just said. So what happens in zero-shot learning is the system has seen a lot of L1 and a lot of L2. It never knows the context when you switch between L1 and L2. Whereas in the artificial data we create, we precisely emphasize on the contexts where you can switch and you cannot switch. And some examples which in the second half we'll doing LMs and embedded word embeddings, we will show specifically, I don't think we have examples in this slide, but we can talk about it, which is that there are significant changes in word sense distributions when you use it in a single language versus in a code mixed language. And that creates a big difference if you have real data.
Hi. In a machine translation case, so you have three cases: pure Hindi, pure English, Romanized, and mixed script. So do you normalize one into each other, or you build three models?
No, for these particular experiments, they are like separate models. Like they are not normalized. Okay. So the three different models we created with this mix, three different types of mixing, and then like see where they are falling. Because, yeah, of course we can do a normalization and pass it to the same system, but there are the issues of like normalization can happen also multiple ways, like spelling variations, and because of this reason. So otherwise, like even when I was showing the example, like the copy model is just copying and transliterating into English. Like if it would have been very good transliteration system which is copying and transliterating, so that could have given exact like target translation, which is not happening because people have like a lot of spelling variation which still our current system cannot handling well. But yeah, for this one there are like three separate models, separate system builds.
Okay, thank you.
I have a question. It's more general questions. So I want to ask you, because I'm so curious about syntactic constraints. Do you think that linguistic constraints is enough to help generating artificial code switching or code mixings? Because when I work with other languages, for example, English and Mandarin, it's so hard because when I read the text, it doesn't make any sense sometimes. Because I feel that, because I think that in different places, people use different ways to code switch or code mix. So I want to ask you for your opinion. Do you think linguistic constraint is the one way to go through, or we should find another way, or maybe there is no exact way to generate artificial code switching sentences?
So this is an excellent question, actually, and the question will be probably clear to the bigger audience after Anirudh covers how we actually generate artificial data. But since you asked and we have time, I will answer your question, which is essentially the way we generate artificial data is using syntactic constraints. This is what he meant when he said syntactic generation of code switch data. Now, what we have seen is, like you are saying, you are absolutely right. Syntactic constraints just tell you the possibility, the space of possibility, all things which are valid, but doesn't tell you the probability. And if you look at any particular geography or multilingual community, these probability distributions vary a lot. So, so for instance, let me give an example which will also answer your question. So the word school in English has many senses. So it's a educational institute. It could be for children, it could be also higher educational institute. In India, though, we use two different languages, words. School is mostly for kids, whereas college is for like what youth school call a grad school. And then school of fish, which is a group, or school of thought. So there are all these multiple meanings. But if you look at English in the code switch data where the word school is used in a Hindi context, almost always the meaning is an educational institution for kids. So if I say Machliyon ka school, which literal translation would be school of fish, it would mean a school in which a fish goes to study. So, and not the usual English meaning. So code switching does have its, in fact, within the same pair of languages, right, there is so much variation. So the way Hindi and English are mixed in India versus the way Hindi and English, Urdu, which is same as Hindi actually, mixed in Pakistan, are very different. We did studies and we saw that there are significant differences. So yes, that's an open problem. We don't have an easy solution. We are trying. I mean, that's what Anirudh is exactly working on, how you can learn from little bit of data the most significant characteristics of code switching of a particular location.
Thank you.
So in the cases of all of this data that you mentioned, both that you used for these models that you just described, as well as in the earlier parts of the talk, when you're doing analysis on how much code mixing is used in different countries, how do you actually detect when there is code mixing, detect what languages are code mixed? Is it like manually graded, or do you use a lookup, or?
So this is all what he's covered, the language identifier that we spent a lot of time building. Right. So that actually we use to annotate every tweet at language level. Now after that, you could just declare that any tweet which has more than one language labels in it is code switched. But we do something more, because that usually gives you very noisy data, because sometimes these named entities are mistagged and so on. So we have some threshold. The paper would describe the exact threshold we use there, but the threshold is at least 20% word should be coming from each language. And also minimum 2 words should be coming from each language. So with these two simultaneously applied, we would narrow down the potential set which our system calls code switched or code mixed. And and we validated, I mean, we arrived at those thresholds and other things through manually looking at the data.
Thank you.
If there are no more questions, we can break for half an hour now. I think there will be coffee outside, right? And we will meet again at 11 here. We are all around, so please feel free to catch us during the coffee break. We'll be happy to chat and answer if you have any questions.